I'm going to talk to you a little bit today about the entity component system and the Burst compiler and C# jobs. Basically, what we've been focused on and where we're going. So, at GDC, we released the Burst compiler. The Burst compiler is really about making C# job code run the absolute fastest it can be, producing the most efficient machine code so that you get the best performance on whatever platform you're targeting. The C# job system is all about making your code run multi-threaded, making it easy and safe to write multi-threaded code. And the entity component system is all about laying out your data so that you have the most efficient linear memory layout, your data is walked the most efficient way, and you get the best performance on the target platform. So that's really our trifecta of performance optimization tools on top of which we're building a foundation for writing super high performance game code. And all of this is available in preview. You can go to this link. And I hope most of you have actually already checked it out. Who of you actually has tried the entity component system, played with it? Okay, great. That's a good half of the people. That's really nice. So since then, we have been working on a couple of new things, really broadening this foundation, making sure that we have the basics to create full gameplay and write it really, really efficiently. So I'm going to talk to you a little bit about what we've been doing in the last 3 months since GDC, since we unloaded all of that stuff on you. Everything we're doing, we're releasing every week, the entity component system. It's in the package manager. You can download it very easily. Every week we make a release, and there's new features coming out all the time. So the first one I want to talk to you about is the reactive systems. So reactive systems are really about making it so that you only do work when something actually changes. So the way we think about it is there are really three kind of events, so to speak, that you're interested in. First of all, you're interested when something is added, a component or an entity is added, when it has been added and now it's removed, and when it has changed. Those are the three things you want to process. And of course, we have principles on top of which we build all of this, and one of the most important ones is performance by default. And performance by default means that, for example, we don't want to have any immediate callbacks. So if a component is added, we don't just call a callback and execute some random system code that does something, because doing that would usually result in quite terrible performance, because we would get cache misses all over the place. We would run arbitrary code, and it would make it very difficult to write any multi-threaded code. So there are no callbacks. Instead, we're simply processing when the system runs. We're processing the things that have been added or removed since the last time the system ran. And we also want to make it easy to use that. So basically, we're following the same patterns that you already know when you deal with entity component system, and just processing all the entities that match a specific pattern. So I'm going to show you a little bit of code of how these reactive systems look. So here we have a rigid body, for example, a rigid body component. It's an iComponent data that you can attach to any entity. And anyone might add or remove this component. You might instantiate an entity with those components on it, or you might destroy it. And what we have been adding is simply this. We have simply added what we call a system state component data. And normally, when you destroy an entity, everything on that entity is gone immediately. If you iterate over it, then that entity is gone. It will no longer be there. A system state component behaves slightly different. It basically, it is, so to speak, owned by the system itself. So if you destroy an entity, we destroy all the components on that entity except the ones that are system state components. They're basically managed by the system itself. And that means the data on them is kept around until the system runs and processes it. So for example, if you want to track all the components, all the rigid body components that have been added, the pattern then goes like this. You have a component data array of all the rigid bodies. And we're basically saying we would like to have everything that has a rigid body and that does not yet have this internal rigid body data component. Because this internal rigid body data component is something that the system adds only when it receives one of these new components. So here we have our added arrays. And then we go through those. We go through all the entities. And here we then add the internal rigid body data component to that entity. So now it has it. So that means the subtractive component here, which says, I only want it if it does not yet have an internal rigid body data. Next time the system runs, it will not trigger for that component anymore. So it's like an event, essentially. It's just attached to the component. And that is super efficient in the entity component system. So there's a very simple way of adding all the, getting a list of the components that have been added. And if you want to, you can schedule a job here, process it any way you like. And everything is, of course, in batch, which makes it really fast. Then we can do the opposite for removal. So for removal, we're saying we're interested in everything that has an internal rigid body data. So basically, everything that this system has already processed, because this system is the one that added this component to it. And then we are also only interested in it if it does not have a rigid body component. So now it's basically the things that have been destroyed. Because if the entity gets destroyed, the rigid body component, because it's the I component data, gets destroyed per usual. But the I system state component stays around until the system processes it itself. So that means we can just go through the removed entities. We process them. We do whatever work we want to do. And then we remove that component from that entity. And that's it. Now we have really efficient processing of all the added things, the removed things, and we do it in batch, and we can write very efficient code to deal with that. The last then is how do we deal with changes? So for changes, there's a couple different patterns, but the most common one is that you write jobified code. You use iJob process component data, which you probably know if you use the entity component system. And here we're saying, OK, we are interested in iterating over all the rigid bodies that are currently in this entity manager. And we're simply adding this attribute here, where we're basically saying, oh, but we would only like to receive the components that have actually changed. So basically, Unity automatically filters out everything that hasn't changed since the last time the system ran, and it gives you those that have changed. And so you only do work on the things that where you need to do work. So that's cool. It's a pretty straightforward, elegant approach, I think, to writing these systems. Actually, Martin, do you have your password for the notes? That'd be cool. Thank you very much. So let's get back to the next area we've been putting some work into. So another really important concept is multiple worlds. So in Unity today, you effectively have everything in one big world. Everything affects each other, and there's a lot of things that you can do if you have the pattern of multiple worlds really built into from the ground up. And what multiple worlds is all about is being able to isolate your data and your behavior and being able to separate them out without, being guaranteed that nothing affects each other. So a world is an entity manager. The entity manager is responsible for, it owns the data, the components, the entities, and so on. And it is also a set of systems. The systems give it the behavior. And together, that is what we define as a world. And you can have as many as you like. You can construct them from code, and it's quite powerful. What you can do with that, for example, is you could, for example, separate simulation from rendering. So you could say, oh, I want to run my simulation code at a lower frame rate. I want to run my simulation code at 5 frames per second, and then my rendering world, I have another set of entities that are basically representing those same simulation entities, but they're just interpolated. So you could run these totally separate at different frequencies from each other and thus get much better performance. That's a common thing to do in a lot of strategy games, for example. Basically, whenever you have a lot of units on screen and you just can't process them every single frame, you need to reduce the frame rate of the simulation. That's one. A couple other really good use cases is when you make a network game, you might want to truly separate the simulation code from the rendering or the presentation layer, just to make it easier to only send the network data for the simulation, or on the server, you might only want to run the simulation code while the rendering is clearly not there. You might also want to have multiple simulations running in the same server process. That can give you a lot of efficiency on the server. So all these things are really quite easy to do when you have access to the multiple worlds. There's one other thing that we have been doing that also really builds on these multiple worlds setups, which I think is quite cool. So we have been trying to unify the concept of streaming. So streaming, I think in practice, when you do streaming, there's really two sort of like broad topics. One is procedural streaming, where we're basically creating things dynamically based on whatever procedural inputs you have, creating foliage or creating whole worlds completely procedural. Or alternatively, you might want to stream scenes, small chunks, so that you have really fast load times and that only a small part of your scene is loaded at any time. So those are, in some sense, they're quite similar. Really, when you think about it, streaming has two parts to it. One part is asynchronously creating a bunch of entities into your scene, right? When you're doing procedural generation, you're just instantiating a lot of entities, usually in the places where you want them, or you want to load it from disk. So you want to take that. You want to take a scene that you have authored in Unity and load it efficiently in. So one part is creating those entities. The second part is then, once that work has been done, and usually that kind of work, you want to do that in a job, you want to do it asynchronously, because maybe it takes longer than a whole frame, right? Reading something from disk can take time. Instantiating and placing a lot of objects with some complex math can take more than a frame would. So you want to do that in a job. The second part then is, once all of that is ready, like once one scene has been fully constructed, how do we make that go live? We want to, in a single transaction, we want that all of that scene data to go live into the simulation world and then pop in all at the same time so that it can start its simulation, rigid bodies can fall down, renderers can start getting rendered, lights, all of these things we want to activate at the same time. So the way we're doing that is we're using the concept of a construction world. So worlds give us full isolation from each other. That means we can just construct stuff temporarily in a world, and when we're done with it, we can move it to the other world where it then is part of that full simulation that is running. So we added support for a new binary format that is specifically made for the entity component system, and that one is insanely fast. Really, it's this format is all about that there is practically no serialization overhead in that format at all. We're basically just loading the runtime data exactly like it is into memory. There's very little patch up. We have a new async file reading API that we're exposing to C#, super low level API, where we can just directly read that data into memory very efficiently and totally asynchronous. And so that covers us on the scene serialization side. There's a lot of work going on making that API really robust and finalizing it. And then on the procedural side, there is this exclusive entity transaction API that is already in the current previews. And with the exclusive entity transaction, you can basically, from a job, create entities, instantiate entities, add components, remove components, destroy entities. You can do whatever you want in that entity manager and basically construct your world completely procedurally. So once all of that is done, you have, in whatever way you liked, you have prepared your streamed scene. Then you can go in and you can use the move transaction entity manager.move entities function to basically take everything that you created in that separated world and move it into the live world. And that function is super efficient. You can easily move 100,000 entities in less than a millisecond. So we spent a lot of time really making sure that performance on that is great, and there's no work on a per entity basis actually going on, so it's really, really fast. So that's what we've been doing to make sort of like a unified streaming system, which I think is really cool. Then there is one very big topic. A lot of the people who have been trying the entity component system know that it's all about blittable data right now, and that means today, if you're using the iComponent data, you can't put a string or an array onto those components. But of course, arrays and strings are super useful. There's plenty of use cases. You might want to have some enemy lists, some inventory items, some targeting positions for your AI, and all of those are, of course, very useful. But of course, we have some principles that we really want to follow with this entity component system. And first of all, of course, performance being a very important one. And arrays is one of those things where performance often goes to die. It's just we never notice because we don't really look so much in detail at it. So the first one is, of course, when we add support for arrays, we need to make sure that these arrays can be accessed from a job safely without worrying, and you can go over a batch of entities, but each one has an array embedded and it can be safely accessed. So we're doing that. The second part, which is a little bit less obvious, is the normal way of dealing with arrays is, of course, you just allocate some memory, either with the garbage collector in .NET, you just allocate some memory, you get a random memory location, or in the case of native array, you just basically, it goes through a generic memory allocator, you malloc some memory, you get back a memory location, and then you have a pointer to somewhere completely random in memory, and then when we iterate over our components and we process them, we just access that random memory and we get a big L2 cache miss, and performance goes to die right there. It's just, when you write code, you don't see that. But of course, these kind of performance hits, they add up. And when we say performance by default, we actually want to solve those problems. So what we're working on is making sure that when we allocate these these arrays that are on components, we know how these components are laid out in the chunks. They're ordered in a specific way, and you're processing your components in a certain order. So we're making sure that the arrays are also laid out in a linear order, so that if you process them in the default order that you're working with components, then the arrays are also laid out in the same way. And that, of course, gives us massively better performance. And it makes it so that you don't have to worry about that. So we're just going to take care of that, and we're going to make sure that arrays have really, really good performance by default. Then we have kicked off work on our first Netcode architecture for the entity component system, and this one is basically where we're implementing a basic first-person shooter Netcode architecture, and our aim is really to make that work at scale. Lots of players in a single session. Yeah, that's we've just kicked off that team now. Then of course there's the Burst compiler. So in 18.1, so the Burst compiler, it's all about getting these massive performance gains when writing C# job code. Right? The Burst compiler is a compiler that's specifically made for C# jobs and the specific subset of code that you can write there. Right? In C# jobs, there's no reference types. There's no managed classes. There's only structs and arrays and nicely laid out data. And so the compiler really allows us to generate the most efficient code for the target platforms and really go beyond what normal compilers actually do. So in 18.1, in preview, we shipped the Burst compiler so that you can look at the performance of it in the editor, because that was the fastest thing to get out, so that you can really understand what kind of performance gains you can get. And many of you have seen 5 to 15x speedups from just turning on the Burst compiler over the mono JIT. And in 18.2, what we're adding is Burst AOT. So essentially, support for desktop, consoles, and mobile. You can now use the Burst compiler, and that means you can actually get these performance gains in a game that you're shipping. It's still in preview, but you can actually build a player that has all of these optimizations enabled. So that work is pretty much done now. And so for the future, there's basically 2 topics we're tackling now that we're focusing on. The first one is really going back and looking at code gen performance, really going through all the patterns that we're using in the entity component system in our math library, and really checking every time that it produces really the most efficient code on every platform, making sure that the instructions we generate are really the absolute best for the type of code that we are writing in the entity component system. And then the second one that we're looking at now is cross-platform floating point determinism. So that's one of the really big promises of the Burst compiler, that we can actually write floating point math code, and we can, with an attribute, simply say, oh, we would like to run that exactly the same on every platform. So between a Linux box and an iOS and an iPhone, we can run floating point math code and produce exactly the same thing. And that, you know, it means that your simulation code will always exactly behave the same. You could make deterministic simulations that are super useful if you want to make a real-time strategy game or those kind of things. You want to make replay systems. So that's a super powerful feature to have built in at the lowest level effectively. Yeah, and then lastly, we have been putting a lot of effort into samples and documentation. So we asked a lot of Unity developers, outside Unity developers, to create some small sample games for us using game objects and mono behaviors. And then in our team, we've been working on converting those to the entity component system to make some full samples of like more like full game code. Like how would we optimally write that? And over the next like couple of months, we will start releasing those as we finish conversion of those. So really to just give you a better starting point for the entity component system. So that's basically just the overview. That's the presentation I have. That's what we've been working on for the last couple of months. And really, the title of this talk was Q&A. So we wanted to leave a lot of time for you to ask any questions that you have about the entity component system, Burst compiler, C# job system. So with that, the mic is open. Thank you. Yeah, so you can. There's a mic there, a mic there. So, yeah.
Anything goes.
Okay, so what kind of plans do you have for inspector support for the new ECS system in terms of inputting data or debugging data, viewing entity data live, and so on?
Right. Okay, so we have already what we call the entity debugger. That's a full tool where you can actually inspect every single entity that exists in an entity manager. You can also see the systems, and you can see the association between them. You can select the system and see what entities does it affect. And also you can go the other way. You can select an entity and see what systems are being affected by that, what systems affect that entity. And it also gives you a quick overview of profiling information. You can turn on and off systems. So that's what we have on the debugging side. We want to put a lot more effort into that. Like we really want to make sure that it's very easy to understand the flow of systems and the data that you have, because the data is so visible now. So we want to make great visualization tools for it. We also have there has been quite a bit of work going on to build a editing tool where you're editing entities directly. This is part of the small runtime effort, and we're working towards merging those together and making sure that we can actually directly edit entities without having to go through what we have to do now, which is basically creating these wrapper components on top of game objects to construct data. So that's really the direction where we're going, a dedicated editing tool. What we really are looking for is, of course, the concept of a hierarchy, a scene view, an inspector, and components that are game objects that you can add and remove. That is, of course, the direction that we're going. It just takes some time to build it, and we're releasing things in preview so that you can follow along and already learn about how to use stuff while we build up all these tools.
Will you be able to hook into that rendering of the data and sort of modify it, like customize it, like the current custom editor stuff?
Yeah, for sure. Like editor extensibility, that's one of the cornerstones of Unity, and it will always remain so. Right. Like if anything, we're making that a lot simpler. Like we have a lot of really cool UI tools, like UI elements that you might have heard about. That makes it much easier to write complex UI tools.
Okay, well, as a node in dev, thank you a lot for that.
Yeah.
Hello. This ECS stuff seems like very handy for linear processing and linear structures.
Yeah.
But what I'm finding hard to wrap my head around is how to convert, say, a tree or a graph that has to be traversed in a particular way.
Mm-hmm. Yeah.
Would you have to because they require references a lot from one component to another?
Yeah.
So would you just use entity references there, or would you rather use a hash map or something?
Yeah. So when dealing with references to entities, generally you just put a entity. The entity is essentially an ID, and it lets you point to any other entity and does the component data in that in a simple way. So there are two ways of accessing it. There's the Entity Manager API, where you can get a component data via the entity ID, and you can set component data via the entity ID. And there's also the component data from entity array, and it pretends like it's an array, but really the indexer, the C# indexer for it, is the entity itself. And so that way you can, from a job, safely access the component data. And that's basically how you deal with graphs. That's how we have done hierarchies. Yeah, and that's probably right now, that's the simplest way of doing it. There is another thing that we're working on, where we're basically working on a graph system, a generic graph system for the entity component system, because we have in the existing Unity, we have the concept of playables that we're using to drive animation, audio, video, and these kind of things, timeline. And of course, we want something similar that is, more, where it's more natural to express graphs in a really efficient way and process them. And that's also another feature we're working on. But for now, definitely just entity references is the way to do it.
So does it get any advantages of these optimizations?
Of using the graphs?
I mean, do graphs and trees get any faster in the same way as a linear structure bit using AHT, ECS?
Right, when using entity lookups. Well, entity lookups, the thing is, when you're looking up an entity by the entity ID, you're basically jumping around in memory, right? You're basically having unpredictable memory access. Yeah. So you always want to avoid, if you care about performance, you want to avoid graphs, because you cannot control the memory layout, and you can't access it linearly, by definition. So I think in practice you want to do it as little as possible, but if you have to, then you use the entity lookup. And
thanks.
Yeah, you're welcome. Yeah.
Hi.
Hey.
You put a lot of efforts to make your memory layout better and linear.
Yeah.
And my question is, do you have internal cache prefetches, or you can provide us a prefetch API to make it even faster?
Right. So the thing is that on modern hardware, if you're accessing your data linearly, there is actually no reason to use hardware prefetch instructions. The last platform where that was useful was PowerPC platforms, and we don't support those anymore. So these days, if the data you're accessing is linear, you actually get worse performance if you put hardware prefetch instructions in there, because the hardware itself knows and sees when it accesses cache lines in a certain pattern, and it starts prefetching them automatically for you. So that's basically why we structure the anti-component system the way we do, so that if that linear memory access happens like that, you just get that performance and you don't have to write prefetch instruction. It's already optimal.
Okay, but I have made tests on ARM platform, which is for all mobiles, and I have about 2 times performance gain on simple matrix multiplication when using PLD. So
okay,
maybe it will be useful.
And this was when actually, and the data was laid out completely linearly.
Yeah.
It's good feedback.
Okay. Well, let's follow up afterwards. I'd love to see exactly the code you were writing for that, how that looks. Okay.
Yeah. Hi.
Hey.
I have 2 small questions. One of them would be about the reactive system. I saw that you guys had this new attribute called changed filter.
Yeah.
And could you explain a bit more about that? Because what does it exactly represent?
Right. So essentially, the way the reactive system works right now is basically it's a sort of like very coarse-grained change filtering. So basically, if anything in a chunk of a specific component type has changed, then that thing gets a version number bumped. So we track which systems have processed that chunk and that specific component type already, and which have not. And the change filter basically skips whole chunks if nothing in that chunk has actually changed since the last time that system ran.
So it's we're actually talking about the contents as well, basically.
Yeah, it's about the contents. Yeah, it's basically if you call entity manager set component data, then a version number gets incremented. If you, in the component data array, access and write to some data, then a version number gets incremented. And the way it's implemented is it actually has no performance overhead on a per entity basis, just on a per chunk basis, and it's literally for free change tracking, so to speak, because it's batched.
All right. For the second question would be mostly about the floating point determinism.
Yeah.
Could you guys also guarantee that for the WebGL builds, or is it not the case?
Well, we haven't looked at doing that for WebGL yet. We have done a lot of research on actually, like testing out how we can structure that determinism, and we have done those tests on ARM and Intel. We haven't tried on WebGL yet, so I don't know if we can guarantee that, because of course there's the browser in the middle, and if we, like the way we make this this cross-platform determinism work with floating point math is that we very carefully omit all our instructions and avoid instructions that aren't deterministic between platforms, and that requires full control over the platform. So I don't know if we can make it work in WebGL or not.
All right, thanks.
You're welcome. Yeah.
Hi. First, I want to thank you for all of this ECS support in the nearest future, because it is a great way to move. And what question I have is about the systems. In my personal experience, when I write the systems, I usually end up that most of them use simple data like integers or so, and just some of them are taking inputs and updating the thing. And I want to cover all of that logic with unit tests.
Yeah.
Are you thinking about like supporting unit testing for systems about an ability to run them outside of Unity editor process? So any thoughts on this?
Yeah, we haven't thought too much about running the code completely outside of Unity, but inside of Unity there is the Unity test runner, and all of the entity component system code has complete test coverage. We have more than 500 tests at this point for the entity component system itself. And the world concept actually makes writing unit tests much easier, because basically in these tests that we write, essentially what we always do is we construct a new world when we run a single test. We add the systems that we want to run, and then we explicitly execute each system that we want to run, and then we check the state that it has produced. And that works really well. And I think also the writer team, Writer is a code editor that personally I use that. That one actually has now integration for actually running the tests from inside Writer, but then actually running them in Unity and feeding back the test results to Writer. So I think that's probably the best way to go. Does that solve your problem, or is there a specific reason you need to be able to run it?
Yeah, it's a good idea to share systems with server side when server doesn't use Unity at all.
Right. So yeah, so that's a good point. So basically, what if I have my server and I want to use the entity component system there? So our strategy about servers is, so first of all, we're building this entity component system so that we can produce really tiny executables. So you saw what we talked in the keynote yesterday about the small runtime. And that's really about making sure that Unity is very modular and that we can deploy only the code that is actually being used. So we think the combination of the Burst compiler, the C# jobs, and then all of the entity manager and the memory management is actually exceptionally well suited to writing server code and making really, really fast to deploy and super efficient server code. Like we can, like on servers, often you have AVX 512 instructions that you can rely on. We can produce really, really well optimized code with Burst there. So I think what we're more thinking about is let's make sure that Unity is a great platform to actually write server code, so that you can also easily share all of your code between the server and the client, and you can easily control it with the systems.
I see. Thank you.
You're welcome.
Hi. First off, just thank you so much for all the hard work you and the team have been doing on this. It's just been great to see it over the last couple of months maturing so fast. It's really good. My question is there a good way yet to handle random number generation? I'm looking and doing some procedural work. Random numbers don't really work very well in the linear serialized nature of ECS, but it's kind of important for a lot of procedural generation.
Yep. No, that's a good point. So, when you're writing multi-threaded code, right, like you want deterministic random number generation, and that's and generally, I think thinking about it in terms of random numbers is maybe the wrong way of thinking about it. Instead, if you look instead how GPUs have developed, what they are doing is basically just really well optimized noise functions. And in the math library, we've added a bunch of new really cool noise functions, anything from Perlin noise to much more optimized but not so good looking random noise. And I think that is a really useful tool for sort of like procedurally generating things and combining noise functions together and randomness that way. And that is very easy to make work in a multi-threaded environment, and it's totally deterministic.
Okay, cool. Tangentially related, is it possible to run ECS worlds purely in editor and not at all at runtime? Linked to procedural stuff, it's really good if you can actually do the generation at edit time just to test things out before you even hit play.
Yeah, I mean, you can construct worlds at any point. You can construct a world completely from code, and there's no restriction when it can run. In fact, in the latest versions, when you create a game object with an I-component data on it, we actually in edit mode we create them into an editor world. You can even see that in the entity debugger. There's a world selector, so you can see there's an editor world being created, and that's actually how, like if you have a game object with this mesh instance render on it, they will actually show up already in the scene view, and that's because there is the mesh instance renderer system has to execute an edit mode tag on it, so it actually runs even in edit mode.
Thank you. That's super helpful.
Yeah.
Hi.
Hey.
First of all, thank you for this presentation. I have a question related to the ordering of the systems. Right now, if you look at the entity debugger, you see the different systems. Are these actually in the order that they are run? And if not, how can I validate whether the systems are run in the correct order?
Yeah. Yeah, so right now they are unfortunately not in the order of the systems, but that's actually something we're working on. We have a pull request that's going in and hopefully getting out in a week or two, which is basically about making sure that we can show all the systems in the exact order that they're running, but then also we are visualizing all the player loop in that tool as well, so that you can see anything else that Unity might be running, like if the animation system is running.
Oh, nice.
So basically giving you a complete overview of the actual order that things are running in.
Great, thank you.
Yeah.
Hi. I had two ECS hybrid-related questions.
Yeah.
Currently, with the component and component data wrappers, if I put these on a game object and I instantiate this game object on runtime, it will always instantiate a new entity and put the components on that. Is there any plans for allowing you to instantiate a game object from a prefab that has this and have the components go to an existing entity?
Right. Yeah. I mean, I tried playing around a little bit with how to sort of like. I mean, what you're saying is basically how do I attach an existing entity to a game object?
Yes.
Sort of overlay
well, the
it
other
together.
way around. So we already have an entity existing with some components that we attach
Yeah.
to it. At some point, we decide to represent it in the physical world using a game object.
Right.
If we instantiate this and it has existing component wrappers on it, it will currently, because of the required component, make a new entity and attach it to that instead of what we already have.
Yeah. Yeah. I mean, there's a couple of different patterns that might make sense for hybrid there. What I recommend is basically just looking at the game object entity class, which is, I mean, it's like basically 100 lines of code that is responsible for when the game object entity component gets enabled, it will register all the iComponent data on that game object with the entity manager. And I think that's probably the type of code you want to replace and come up with something that makes more sense for your use case. We just haven't really found a good way of exposing that in a general purpose way. But I understand the use case.
Because currently it's a required component, which means even if I want to replace it and not make a new entity but use an existing one, I can't.
That's a good point.
Yeah, we should take that afterwards.
You could disable it, I guess. But yeah, I guess we should just make a small sample with that kind of setup.
And a second quick related question. Currently, you only have one physics world for doing physics, which means that if I want to have anything use actual colliders and collision, it doesn't really work very well if I have two worlds which simulate, for example, a server or a client.
Yeah.
Is there any plans to have this split up, or maybe an ECS-based physics engine?
Yeah. So, I mean, right now this is just a foundation that we have, right? And like that means you can write game code, and we have the bare bones. You know, we have a mesh renderer, and I mean, we have all kinds of utility methods that you can call, but essentially, in the pure world, there aren't a lot of features yet. So the plan is definitely that over time we're going to make all the features that today exist in Unity also available through pure iComponent data, and as part of that, really upgrading them to, you know, take advantage of the Burst compiler, make everything insanely well optimized, performance by default, deterministic simulation code, and so on. Like really making sure that we follow all these principles as we go through it. That takes time, of course, but definitely a physics engine that fits into this new world and our new principles is absolutely something we're doing.
Thank you very much.
Actually, for physics in 18.3, due to the prefab changes, it is actually possible to do multiple physics worlds.
Thank you.
Yeah.
Hello. Thank you for the presentation and for the system. Looking forward to using it in production in the future. I have two questions about ease of use, reducing boilerplate code, and so on.
Yeah.
The first one being, right now, you can't create entities, add components, remove components, etc. In jobs due to memory layout, I guess. Are there plans to somehow fix this?
Right.
Because right now, to use jobs and to create new entities, there are a lot of really, I don't want to say ugly, but it is code with copying to arrays and so on.
Right. Well, so actually there is a way of doing it, which is what we call the entity command buffer. So the entity command buffer is basically it's basically a class where you can create entities, destroy entities, add components, remove components. And the reason we created the entity command buffer is because when you add, remove components, you're basically doing a structural change. And a structural change means, if I add a component to an existing entity, that entity data might move around in memory because we have this high performance processing where we need to guarantee that data is laid out linearly. So we move data around to then get performance speedups. But if there's already jobs running that are accessing that data, it would be impossible to guarantee correct behavior. So that's why the pattern that we're going with is instead that use the entity command buffer, and at schedule time of a job, you're basically declaring when this entity command buffer should be played back. So basically, you're basically in your job, you fill it up with whatever components you want to create, destroy, add, instantiate objects, and so on. And then at a later time in the frame or next frame, when we have a sync point on the main thread where there's no jobs running anymore, then those components get added and removed.
Are you talking about post-update buffer in system?
Yes.
Or is it?
Yeah, so there's the post-update commands. You can use them. That one is made for the main thread. And then for jobs, there's a barrier system where you can then basically specify exactly at which point in the frame does it run. And that's super important because that way the sync points can be reduced to very few, which is very important to get the most parallelism.
But I find that it is still slower than doing code like it's in Boyd's example. Like in a job, you just compute what entities do you want to create, fill an array, and then create entities in a batch with.
Right.
Well, it's still command buffers, in my experience, are still slower than that approach.
Okay. That's interesting. I'd love to see a sample or something where you can
I guess I can post it on forums.
That'd be great. I mean, like if you post it on the forum, like a small sample where we can reproduce the performance issues. I mean, definitely the goal with entity command buffer is for that to be as fast or faster than using the entity manager directly. That's the aim.
Okay, and a small question, second small question. There's when you, it's like systems like doing the queries to some kind of database.
Yeah.
I want the entities with these components and so on. Are there plans or thoughts about doing some supporting more complex queries, like I want entities with components that are equal to something or something like that?
You mean like where you write your own code for filtering?
For example, right? Or if my entity references another entity and I want something like join.
Yeah. I mean, basically, we started experimenting a little bit with the reactive systems about being able to produce an index list, which is basically a filter that you could pass into the component group, and then you would only process those entities.
Mm-hmm.
Yeah, we kind of experimented with it, but then didn't do that much more on it, and just focused on getting the basic add, remove, change systems going. But I think that's definitely interesting to support filtering where you actually have code that produces the filter. I think that's quite useful.
Okay, thank you.
You're welcome.
Yeah, we're done. We have to go.
Really?
Yeah.
We can take 3 more questions.
We can take them outside.
We can?
Yeah.
All right.
So just the people that have questions will be outside for like 10, 15 minutes, and then you can ask us out there as well. Okay. Sorry about that. We ran out of time. Thank you for coming.